In part 4 of our example, we're now going to calculate the long-term deflection. Concrete is unusual in that it creeps, and so if you do not increase the load but just wait, the deflection will increase over time, and that's due to creep. And only concrete creeps, steel doesn't creep. And so one of the strategies, if your creep deflections are too big, one of the strategies to mitigate that is to put in compression steel. We talked about this when we talked about compression steel in beams. And so we are doing the immediate live and dead load deflection, and then we're going to multiply that by a multiplier. And what we want to know is the deflection due to the load that is always on the beam. And so obviously dead load by definition is always on the beam, but there's a certain percentage of live load that never goes away on average. And I've taken that average to be 30% of the live. This is your engineering judgment. And so I'm saying 30% of that live load is stuff like desks or things that can move but never move. And they're always there on average. And so I'm saying that 30% of the live over the next 5 years on average will always be on our beam, and that load will be causing creep. And if you take the dead plus 30% of the live moment, you come up with these values. These are smaller than the full dead plus live. And these represent the loads that are always on the beam 24/7. Oh, by the way, 24/7, 365, that doesn't make any sense, right? It's 24 hours per day, 7 days per week. There's not 365 weeks in a year. It should be 24/7, 52. But that doesn't sound right. Anyway, you understand. This is a load that is always on there for the next 5 years. We're going to use the moment of inertia for the full dead plus live. We're not going to do the calculations again using dead plus 30% live. And this is the reasoning. When you've put the full live load on the beam at some point, okay, you've cracked the beam. Maybe on opening day of the building, you get a big crowd. You're ribbon cutting or something, and you get the biggest load there ever is on that building, and it's cracked on day one of the building. Everybody goes home. It's still cracked. Just because people leave the building doesn't mean the beam's uncracked. Once the beams are cracked, they're cracked. And so the moment of inertia is 3224. It never goes back up when you take the load off. Remember, the less load, the higher the moment of inertia, but it's irreversible. So if for some reason you had an unusually high load in the building one day, I don't know, it's like, let's say how many people we can fit in the room or something like that. Or one time in our storage room, I had to help stack the copier paper, and that paper was stacked 8 boxes high, and they were heavy. And I calculated the load per square foot. It was way higher than the 40 PSF that room was probably designed for. I'll bet you those beams cracked, and they didn't uncrack after that. Anyway, we're going to take the effective moment of inertia from the dead plus live load, full dead plus live, that we calculated earlier in the previous video. It was 3224 inches to the fourth. Then all we're going to do is use this equation again, this approximate equation. We're putting that 3224 in for the I, but for the moments, we're using these dead plus 30% live moments. You put everything in there. Again, if you want to see the numbers crunched, you can see this appendix video, the 5th video after this, and it comes out to 0.35 inches. So if you put 30% of the live and the full dead on the beam, it would deflect right then and there 0.35 inches. What we want to know is how much over the next 5 years this deflection will increase. And the multiplier is C divided by 1 minus 50 rho prime. And rho prime is just like rho. It's the area of steel over BD, but it's the compression steel. So the amount of compression steel divided by BD is rho prime. And you can see as rho prime gets bigger, you get, what's that? You get a smaller denominator. Is that right? I'll have to double check that. It's supposed to be as rho prime goes up, lambda gets smaller. So let me double check that if that's right, because right now it's making it bigger. So let me double check that. But in our example, rho prime was 0. I'll bet you it's 1 plus 50 rho prime. Let me double check that. Anyway, because the rho prime is 0 in our problem, lambda is 2. And the multiplier is 2. So what that means is this 0.35 inch deflection immediately over the next 5 years increases by double. And so the long-term deflection is 0.7 inches. So you start off with that 0.45 inch live load deflection, and over the next 5 years it increases another 0.7 inches. And so the total long-term deflection, live plus time dependent, is 1.15 inches. And that's the end of this problem. Let me double check that rho prime equation and come right back. Okay, I just checked the code book, and yes, indeed, it's 1 plus 50 rho prime in that denominator. Let me go back to that. Okay, so that it's 1 plus 50 rho prime. So for example, let's say rho prime is 1%. So that would be 1 over 100. So that'll be 1 plus 50 over 100. And so the multiplier would be 2 divided by 1.5 instead of 2 divided by 1. And this makes more sense. As rho prime goes up, that lambda goes down. Okay, that is now the end of this video and this example. There is the 5th video. It's sort of like an appendix where I go through all the nitty-gritty details of the calculations. If you trust me with those 0.14 inches, 0.59 inches, you don't have to watch it. But I assume that when you do it for yourself, for your homework, you're probably going to want to watch that last video to see all the little details. But other than that, that's the end of this example.